In our examples up until now, we've looked at finding the probability of a single event. In the next several examples, we'll look at how you can go beyond that to find the probability of 2 events or more events, so 3, 4, or 5. And we're going to look at this in 2 ways initially. We're going to look at it with tree diagrams to kind of get a sense of what's happening, and then we'll look at using a formula, which is actually an easier route in the long run. But the tree diagram helps us understand it. So that's what we're going to start with. So let's look at our first example of tossing a coin twice. So that would be 2 events because we're tossing the coin twice. To investigate this, we're going to draw a tree diagram. A tree diagram is called such because you branch off with your options. So our first coin toss, we would have 2 options. We're going to branch off to each. We would get a head or a tail. Now, in our second coin toss, it happens after we've performed the first coin toss, so it branches off after the options for the first coin toss. So I might have gotten a head in my first coin toss, and then there are 2 options after that for the second toss. A head and a tail comes after the initial head. Same thing could be said for the initial toss of a tail. Once you have the initial toss of a tail, you toss again and you get either a head or a tail. So if I look back through these branches, I can actually see all the possibilities for both tosses. I could have gotten 2 heads. Another branching off would be getting a head and then a tail. Another option would have been starting with a head and then starting with a tail rather, and then getting a head. And then my last option would be to get 2 tails. So you'll notice here that there's 2 ways that we can get one of each, but we get them in a different way. The first is with a head and then a tail, and the second is with a tail and then a head, and those are considered different in terms of our sample space. So our sample space for tossing a coin twice would include getting a head twice, getting a head and then a tail, getting a tail and then a head, and then getting 2 tails. Those would be our 4 options, our 4 outcomes in our sample space. Once we have our sample space, then we can use our rule for finding a probability to actually determine the probability of getting heads both times. There is only one way to get heads both times out of 4 different options. So this would be a probability of 1/4 or 25%. So you have a 25% chance of getting heads both times when you toss the coin twice. In our second example, we're going to look at drawing 2 marbles, so again 2 events, from a bag containing 2 red marbles and 1 blue marble. We're going to do this without replacing the first marble before drawing the second. So let's look at the situation with a tree diagram. Our first branching, we have all 3 marbles in the bag. So I've got 2 red and 1 blue marble in the bag in my first draw. So what I'm going to have in terms of a branching is 3 branches. I could have a red marble come up, and I'm going to call it red 1, and a second red marble come up, red 2, or I could have the blue marble come up. So this is like red 1, red 2, and blue. That would be my first draw of the bag. There's 3 marbles. But once I draw 3 marbles, or 1 marble from the bag of 3 marbles, I'm only going to have 2 marbles to choose from. For instance, if I draw one of the red marbles, like in my first branching, I only am going to have 1 red marble and 1 blue marble left to draw from. So I could label that specifically the second red marble left to pick, and then the blue marble. So as I pick the first marble out, that changes what's left to pick in the second. So my bag has changed when I go to my second pick. Let's continue on with our tree diagram. If I had picked the second red marble, what would be left to pick from is the first red marble and the blue marble. And if I picked the blue marble, I would have the choice of either red marble to pick from, so red 1 or red 2. So when you look at these options, I could have the 2 red marbles be picked. I could have the first red marble and the blue marble picked. I could have the 2 red marbles picked a different way, the second red first and then the first red second. I could have the second red marble picked and then the blue marble picked. And then I could have the blue marble picked with the red marble, first red marble, and then I could have the blue marble and the second red marble picked. So my sample space would include all 6 of these options. So this would be the sample space. Now to find the probability of drawing 2 red marbles, I would think about how many ways there are to draw 2 red marbles. There's 1, 2 options for that. So I would have 2 options out of 6 total things that could happen in this scenario. 2 out of 6 is the same thing as 1/3, or 33.3% chance. So in this example, if I'm going to draw 2 marbles and I want to know what's the chance of having them both be red, that is a 33.3% chance. And that's based on looking at all the situations with the tree diagram and then using the sample space created to find the probability. Now, the reason we don't use tree diagrams all the time is you can imagine that these tree diagrams get quite complicated if we have more than a couple of options. So say we had a bag of 20 marbles. Trying to draw out 20 marbles for the first pick and then 19 branching off for the second pick for every one of those 12 marbles would be a very, very big diagram. So we'd like to have another way of doing this. That other way is what we sometimes refer to as the multiplication rule. So here's going to be our calculation when we have 2 or more events. Let's start with 2 events. Say A and B are the events that we want to look at. The probability of both events occurring can be calculated by multiplying the individual probabilities with the caveat that you must consider whether the occurrence of the first event affects the second. Okay, so in brief, the probability of the 2 events occurring, so A and B, is going to be equal to the probability of the first times the probability of the second, with the understanding that you have to think about if anything has changed because the first one occurred. So basically you're multiplying the 2 individual probabilities together with the understanding that with the second one you have to think about whether something has changed. So let's look at the first example that we looked at with tree diagrams, tossing a coin twice. What's the probability of getting a head both times? So that would be like a head and another head. So in calculating this, I'm going to multiply the probability of getting a head in my first toss of a coin, and then multiply that by the probability of getting another head on my second toss. Well, the probability of getting a head in just a single toss, there's only 2 things that can happen when you toss a coin. You either get a head or a tail. So the chance of getting a head is 1/2. Now, when you go to toss the coin a second time, think about that coin. Does anything change about the coin between your first toss and your second toss? No, the coin is still the same coin. Nothing has changed. So the chance of getting a head is still 1/2. So nothing changes about the coin in that second toss. Nothing changes here, so my probability doesn't change. The coin stays the same. So my probability is the same. Once we have the 2 individual probabilities listed there, I'm going to multiply them. And a quick hint for multiplying these, take each one separately. So we would say 1 divided by 2, and then times 1 divided by 2. So take each one separately, entering them in the calculator with the times in between them. And this would be 0.25. You could also, if you wanted to, write that as a percent, 25%. Or if you're feeling comfortable and you want to show the fraction answer here, you could multiply straight across. 1 times 1 is 1, 2 times 2 is 4, so you would have 1/4, which is the same thing as 25%. But for most of our examples that have more complicated numbers, I think it's going to be easier just to throw it into the calculator as 1 divided by 2 times 1 divided by 2 to get that 25% coming out. That is the same answer we got when we used the tree diagrams. So we've kind of confirmed that this multiplication rule does work if we use it properly. Now our second example, let's see if how the multiplication works here. So remember in the second example we had when we did tree diagrams, we were drawing 2 marbles from a bag containing 2 red and 1 blue marble without replacing the first marble before drawing the second. So we wanted to look at the probability of a red marble and another red marble. So I'm going to multiply those 2 individual probabilities together. Now the chance of drawing a red marble initially, remember there were 2 red marbles in the bag and 1 blue marble. So my chance of drawing a red marble initially was 2 out of 3. That's the first pick. But what happens is that once I've drawn that red marble, my bag is going to change. My bag will now only have 1 red and 1 blue in it. So my bag has changed. So my second chance of getting a red is not the same as it was initially. Because my bag has changed, the chance of getting a red is 1 out of 2. So you have to keep in mind when you calculate your second probability, or you put it in there into the formula, has something changed about the scenario that would make that probability calculate differently? And here the bag has changed, so I have to think about how the bag is now different and calculate the probability of getting a red with that changed bag. So now doing the calculation, start with the first fraction, 3 divided by 2, times the second fraction, 1 divided by 2. And that gives us a value of 0.33333, or 33.3%. That is exactly what we got when we looked at using the tree diagram. So this is the formula you're going to use most of the time because tree diagrams are a little inconvenient for a lot of examples. But this multiplication rule will work as long as you consider the possibility that in your second occurrence, that second event, that the probability may need to be adjusted compared to what you were working with in the first probability. So this is the multiplication rule for probabilities.